Hey there guys, Beans Brother here to present Lab 1 for the electric tapes. Now here's an appendix where we're going to start out with an introduction, then move to data and observations, then finally some Glowscript and final observations. Here in the introduction we need to first start out with that we're going to be using some clear tape to demonstrate the transfer of electric excess charges. And how we're going to do that is just simply ripping one piece of tape off the other, and we're going to gather excess charges off of that. We're going to take those two charged tapes together, and when the tape starts to float on one side, that means that force of gravity is equaling out with force of electric, where we could then gather some data about it. Now, some of the principles that we're going to be using is the Coulomb's law, and that way we could calculate the force of electric, and we're also going to assume Newton's second and third laws for equal and opposite effects, and also calculating the force of gravity. Now, for the lab results, we're going to go ahead and use some assumptions, some of which will be called as this following. Ignore air resistance on a moving object, since it is more than likely going to be negligible, unless it's very windy inside. Treat a long tape as though it was a point charge, and make sure that when you do that, make sure that all of the charges are going to be centered at the center of that long piece of tape. Now, assume that each of the U-tapes that you made had about the same amount of charge, and it was about distributed evenly across the entire tape. Now, what is the length of one piece of tape? 0.2 meters. If there's 1 gram per meter, that means you have 0.0002 kilograms. What is the distance between your two tapes when one began to float above the other? The answer is about 3.3 centimeters. When we were calculating the magnitude for the gravitational force, now all we have to do is simply multiply our mass, which we did earlier, by our gravity, and we get 0.049 newtons. So that means that if the electric force and the floating tape are equivalent forces to make the tape float, then that means that the electric force must also be 0.049 newtons as well. So with that out of the way, we can now talk about another important idea. What is the magnitude of charge on one of the pieces of tape? Well, the answer is that if gravity and electric forces are counterbalancing each other, we could set them both equal and say that they net out to be zero. When we do that, we could go ahead and geometrically arrange everything, including the assumptions that we made earlier where we said that each of the point charges could be idealized as Q. You know, you rip off one piece of tape from another, it has to transfer charges from somewhere. They both have about the same. So now we get Q is equal to 1.5 or 1.54 times 10 to the negative 8 coulombs. And so to find electrons on the tape, we take the calculations we just did, divided by the charge of one electron, and we get about 9.63 times 10 to the 10th electron. Then we simply find the area of both the tape and the atom to find the amount of atoms that we have by the ratio of those previous latter two. We get 4 times 10 to the 17th atoms. Now we're going to take a ratio of the electron to atoms, and we get 2.4 times 10 to the negative 7th electron to 1 atom from those calculations. And when we do that, we could go ahead and put it into our computational model. So let's begin. Alright guys, we're inside of the code now. So first we initialize all of our constants from previous calculations. Here we go ahead and create our objects along with their respective vectors and all the super duper fun colors, and we have our print hello world to go ahead and just be a confirmation that we started our program. Now here we're just going to initialize all of our calculations that we use and know and love. So here, for example, we have the distance between the two particles that we initialized earlier, and now we're just going to calculate for the force electron and the E field, and over here we're going to see that the force of gravity is just going to be equal to the weight of our objects, right? So now, while under this iteration loop where earlier we defined the force electric here and we've defined the force of gravity as the weight, while force electric is less than force of gravity, I want you to reiterate all of these calculations that we did earlier at the initialization stage. The only difference now is that we want to move that particle up, and as we do it, we're going to go ahead and scale our forces accordingly with the arrows. So now let's look at that when it runs. Now this red particle represents us coming closer towards that other charge tape, and as we get closer with our own charge tape, we're going to produce an electric force. Now that electric force is being represented by the red arrow, and when that red arrow is going to equal out to that blue arrow, we're going to stop our iterations. And that iteration says that we're going to stop at a distance of 3.3 centimeters, which is very, very close to what we got previously. So that's all for today. And some final remarks. What if the electrons had positive charge and protons had negative charge? What would change about the observations that you made about the tapes and other charged objects? Well, the answer is that nothing would really change. Like charges would still repel and opposite charges would still attract. Why is it important to handle the charged tapes as little as possible? What happens if you have them in contact with your hands or other objects? And the answer is that electric charges tend to spread across the surface that they have until equilibrium. So the more neutral hand would spread the charges around and practically dissipate the experiments into the body and the environment. Right, everyone have a beautiful Beans Day, and I will see you guys in the next lab.